Our goal is to create an educational setup of a wireless power system to characterize and demonstrate the properties of an antenna system. This setup will also educate the audience on potential antenna application as well as engineering electromagnetic materials or metamaterials.
The wireless power system is based on a strong magnetic resonance coupling between two spiral coil antennas operating at MHz frequency. The system is based on the principle that two resonating coils tuned at the same frequency can effectively exchange energy. In addition, we will implement a hybrid metasurface with zero permeability at the center and negative permeability at the edges to help focus the energy or steer the beam width from the transmitter to the receiver. The principal interaction of the system occurs between the transmitter and receiver coils. The transmitter coil is excited by the driver loop, and this interaction works as a step-up transformer to increment the magnetic field. The receiver antenna will intercept the change in the magnetic field and will generate an electromagnetic field. Then the load loop will act as a step-down transformer and it will be connected to the load. The other purpose of the driver loops is help to match the impedances.
For demonstration purposes, we built an adjustable structural base where we can place the transmitter, receiver, and the driver loops to slide them in the range of 5 centimeters to 1 meter, varying the distance between the transmitter and the receiver. This will vary the coupling coefficient between the antennas. By varying the distance between the driver loops and the coils, we can match the input and output impedance for maximum power transfer. To extract the resonant frequency of the coils, we use vector network analyzer to get the reflection coefficient. To tune the driver loops at the same resonant frequency of the coils, we use the coaxial cable, which act like capacitors, since these are more stable at higher frequency and have low losses.
Using PSPACE, we can perform simulation to obtain the expected input and output power of the system. Also, we use MATLAB to plot the S21 of the system based on its transfer function and varying the distance between the transmitter and receiver, which is the coupling coefficient to 3, and the frequency. By doing this, we can obtain the expected behavior of the system.
The hybrid metasurface will be implemented to enhance the performance of the system. Since we are working with a hybrid metasurface, one part will have negative permeability at the resonating frequency of the system, and the other part will have permeability close to 0. Our design consists of a unit cell of 4 cm by 4 cm, 10 turns, line width of 1 mm, and 0.5 mm spacing between the lines. By setting up an inverter to increase the input power at the resonant frequency of the system, we are going to be able to increment the output power. Using LEDs on a ladder, we will be able to visualize how the output power varies as the distance from transmitter to receiver changes. Also, by implementing the hybrid metasurface, we will see how it enhances the performance of the system.